Hi everybody and welcome to this video about WAL malware analysis flow of AgentTesla Malware. As one of you guys asked me about help with this sample, I basically jumped to it because I never show WAL malware analysis flow, usually some tricks and tips about some specific issue, but in this case, in this video, I will cover WAL malware analysis, which basically contains initial vector of compromise, which is a Microsoft Office document. This Microsoft Office document basically has external reference, and this external reference is another Microsoft Office document RTF format, and this RTF format is exploiting vulnerability equation editor, I think, and basically next stage of this RTF is basically shellcode, which is inside this malformed RTF document, and so we will be analyzing also the shellcode, and after that we will jump to the last stage, which is also downloaded, and the last stage is wrapped AgentTesla, and AgentTesla is basically packed in Visual Basic code, and I will show you how you can basically very fastly unpack it and obtain the obfuscated form of AgentTesla, and after that we will deobfuscate it. I will try to do it in a fast way, but I would also try to cover some more possible approaches. Yep. So let's jump to it. First of all, I obtained this link to the sample, and it's available on Anyrun. The link to the sample will be included below this video, as always. And you can see immediately I highly recommend download the sample if you just try to do it by your own, but I also recommend to download the PCAP, because if you, as you can see, the sample is like 4, 5, 6 months old, so the command and control server will be down, and it's down, I will show you later. So if you download the PCAP, here is all the next stages which are downloaded here. So we will just grab it from the PCAP. And what you can see here, you can see here that the Microsoft Office Word was spawned, and something called EQ and EDT32 was spawned too. It's basically equation editor. Basically, if you have a Microsoft Office document, you can just insert the equation table, and this equation table has vulnerability, I think, from the year of 2017, but you can see it here. If you open it, you can see here is equation editor starts application and CVE 2017 11882. Nice. So what you can see next, you can see here that the equation editor is basically spawning new processes called VBC, and check the command line VBC, and so probably something which was what was downloaded, and you can see here all the stages which were downloaded. So I highly recommend to download the PCAPs. You can see first of all, you can see that here is some HTML. If you check the HTML, it's a redirection to some IP, and from the IP you can see that next stage is downloaded. If you check the next stage, it's some kind of RTF document. But what I think is quite interesting about this analysis, and why I choose to help, well, I choose to help because I'm just quite trying to be a good person, but this RTF document is some kind of not only exploiting the vulnerability, but it's also some kind of encrypted form. So many tools are not able to properly parse the objects of RTF document, and I will cover it later. So here is the next stage, and which is basically the external reference. And here you can see the last stage is some kind of executable. Nice. So highly recommend download the PCAP and download the sample. Okay. Now I'm in my first VM. I will also use another VM because of Microsoft Office. So first of all, we have here the downloaded sample here. So let's unpack it. Password is infected from anyone. Nice. and you are here. Basically, what I suggest to start for everybody, every time confirm that you know what you are dealing with. Basically, the format of the file. So just use your favorite hex editor, and you can see that it's some kind of archive. And you can see the content is some XML files. So it really looks like some kind of Microsoft Office document in format OpenXML. Nice. What you can do next is basically use my favorite tool, Detect Easy. Absolutely phenomenal. You can see here that it's a archive, but you can switch the detector for as a nose file detector and not Detect Easy. And you can see it's because nose file detector is using some more heuristic signatures, and you can see it's Microsoft Office Word. If you check the content, I really love this tool. You can see in this content that that's basically Microsoft Office Word. docx format, OpenXML. Nice. So what you can do now? Now you can run PowerShell, and let's try some very good tools. My favorite when I'm dealing with documents are basically Oli tools and tools made by Didier Stevenson, very, very well-known science instructor and absolutely phenomenal person. So if you, first of all, I will try to use Oli ID, and on this sample. Even though this file is not in format of OLI2 stream, like OLI2 is a specific format of older version of Microsoft Office documents like doc, PPT, and XLS. Uh, Even though it's not OLI2 format, it's able to tell you that basically this document file format is Microsoft Office Word 2007 and later. Why? Because it's the docx and format is OpenXML. Nice. You can see that there are no macros, there is nothing encrypted, and what you can see here, external relationship 1, high risk. Yeah, that's basically what we want to check. And what is the URL, the external reference? And here is basically nice hint. Use Oli object for details. Nice. So just jump to Oli object and again download. And you can see that it was able to parse out the external relationship reference. Here is the URL. Okay, this is one thing. I really appreciate it, but what I usually do, just copy this, and we have to confirm it in some array. So I usually use at least 2 tools for the same thing. Trust, but verify. Extract files, okay, because as it's basically format of archive, you can extract it as a normal zip. And you can see here is the content, but I like to use dngrep, where you would like to search for strings in all files in this directory. I would like to search for this URL and search in all. You can see here is immediately one hint. Yep, and you can see basically it's some kind of frame. Object is frame, and target is this URL, and target mode external. Nice. You can see also this ID. If you try to search for this ID, you can see more relationship between this object, which is basically downloaded as an external reference. And you can see here other things, that it's a frame, and other things. But what we needed is basically the URL, which is somewhere here. No, here. Okay, so here is some external reference. copy it, and again we can just run PowerShell. And what I usually like to do immediately, it depends on the time I have, so we can just do respond and invoke web request. We will try to download the external reference, but as I already told you, command and control server is probably down because it's quite an old sample. URI. And user agent. Highly recommend to change your user agent because many command and control servers are just checking the user agent if it's really downloaded by Microsoft Office Word. So we can just search for Microsoft Office user agent and just grab for example this first one. Everything is better than the PowerShell. Yep, and copy it here and run it. If you check the response, you can see it's empty. Yep, it's empty, no raw content, it's just empty. So basically the server is up, but there is nothing to serve for us, even though we changed the user agent. Remember, change it, because it's really trivial to just on the server side, on the command and control server, just checking the user agent to just throw out all the tries to analyze this sample and other things. Okay, so but for this that we can download it, I already downloaded and prepared it here, the pcap. I have here the pcap from the environment, so you can just I think that we can delete this one and just run network miner, my favorite tool when I'm doing network forensics and other things. But it's a really nice tool when you want to fast extract some files from HTTP and other things, FTP and SMTP, FTP, other things. So first of all, you can see here are 3 files. Nice. First one is the HTML document. I think that is the document saying the redirection. So if you open the file, no, I don't want to do it this way. Open folder, and here one editor, and check it. That's move permanently and redirection to this IP. So let's check the IP. If you check here, you can see that it's sorted by time, and basically this is the next stage payload, which is the external reference. And if you check it, open folder, you can see it here nicely. And yep, just copy that because we will use it. And this is the last one. Open folder, and you can see it's an exe file. Let's confirm it quickly. Nice. So first of all, the Microsoft Office document is run. The initial one, it's basically downloaded external reference, which is RTF document. We will confirm it later. And this RTF document is exploiting CE 2017-11882, I think. And this exploit is basically shellcode, and this shellcode is downloading this last stage payload, the exe file, which is probably wrapped AgentTesla. Nice. Okay, just copy that because we will be using it later. Nice, we have here all what we need. Now, what you can do, let's confirm it quickly, or I will jump to my second VM. Here, And you can see here is the sample of a malicious document, the initial one. And if you try to basically run it, you will see that it will try to connect to the server I already mentioned we get from the Oli tools and other things. So let's start to capture with Wireshark and try to run it. And yeah, I think it's enough. Close it. And what you can see, filter HTTP, and you can see trying to connect to, yep, you can see here redirection and nothing. Follow HTTP stream, and you can see here, and the IP address or the host is bit.do, and this is the redirection. Okay, so nice. We just confirmed it quickly. Delete it, yes, but we don't need the next stage payload because we already have it. So it doesn't matter if it's down. So let's jump back to my first VM and we can continue. So we have this dot file. I think that it should be RTF document because the exploit of a CVE on 2017-11882 is basically common, and as I already show you in the any run that it should be some kind of malformed RTF. Let's open it in a 101 editor or your favorite hex editor. You can see here is the strange magic string because it should be RT1 I think, but it doesn't matter. So it's some kind of malform because you can see it's basically there is some garbage and maybe garbage, maybe some shellcode. We don't know yet. And you can see here some objects. Object link, object update, which basically this basically resolve that you can't see some pop-up window that the Microsoft Office is trying to download something. Yes, so what we can do now, we can also use, again, detect it easy, and it will tell you that basically it's a RTF document. Nice, again, detect it easy shines. So now just run PowerShell, and we will be using my other favorite tools, again, from the Oli tools repository, and I will use just RTF. First of all, I will try to use RTF dump. And okay, we will be using converting to hex decode. We'll be selecting some item, and that's probably all. So RTF, and first of all the dot file, and you can see it's already in some kind of strange form. You can see here are some object data, and okay, for you in normal situation, if it's not malform like this, you should investigate the object data. All of these, especially the one which are large. You can see the length is 6763. But in this case, you have to investigate the item 1. Don't ask me why, but in the item 1 is basically the shellcode. I will also tell you how I found out it later. So basically, if you just try to select item 1 and hex decode, you can see something like this. This is quite normal that you see something like this, but be careful and check it here. Equation 3. So this is basically the object of equation table, and somewhere here starts the shellcode, but we don't know it where exactly. But what you can help you, my other favorite tool is RTF object dot, and tell me. RTF object is able to parse out some two objects, and it will tell you that, hey, not well-formed Oli object. Okay, just try to extract them, because if you check the help for RTF object, you can basically extract all objects like safe objects, all, and D as a dump dir. So dump directory. So we will just do options s all, save all, and the current directory, but folder will be dumped, and file name is dot, and it's dumped. Nice. We can check it and just show me in the 1.1 editor. And first object is empty. Nice. So we just don't bother with this, but this is something what you already saw. Equation free and something here. So we will be working, basically this is the same what we saw before here with the RTF dump. Nice. So we can just continue with this 903. 903. This is just basically empty, and this is our interesting one because it contains the shellcode, but we don't know exactly where. If it will be quite a nice form of RTF, we can basically extract the shellcode easily, but now it's quite more difficult. But no, for us, don't worry. So first of all, we can try some tools. My favorite one is a source search from Didier Stevenson, because source search has something which is called W to search with embedded wildcards, and these wildcards are also able to find some typical shellcode starts and other things like prolog, epilogs, and finding the EIP address and other things. Typical instruction in assembly, encode it into bytes, and it will try to find there somewhere where the offset of from the file is basically. So we can use the source search with the option of W, and the file will be the one we extracted here. And what you can see, everything is just telling you that the offset is BB. BB is offset of something which probably source search thinks that it could be the start of the shellcode. Nice. So what we can do now, we can basically try to open it in 101 editor, go to BB, which is somewhere here, yep, BB, and just delete this first things. If you check it, E9F901, E9F1901. So this is probably start, as source search is telling it to you. But we can confirm it later, it will be quite easy. First of all, I don't want to just try that pretend that I'm just trusting all these tools because I didn't make them, but they are very, very awesome. But we can just basically rename it to the shellcode.bin. Nice. Let's throw it to IDA. It's basically the RTF document is trying to exploit equation table, equation program, and this program is 32-bit application, so it should be 32-bit shellcode. Okay, binary, yes, 32-bit. Okay, and select all. Okay, edit, select all, unidentified it, and just go to here and convert it to code with C. Jump to the location, and here is another location. Call. You can see that we start from the first, from the offset of BB as source search told us, but you can see here is only the jump. Jump, and what is going on here? Call, text view, and you can see here is the code, call, you pop EBP. What happens here? Basically just call the function and return address, which is address here, this one, is basically pushed on stack and it's popped here to EBP. So this is basically address where the location, how basically shellcode is trying to find the location where it is in the memory. And you can see another jumps basically for some obfuscation. You can see here is some adding to EBP, location another one, another one. And here you can see basically some counter, and because it's the location of the shellcode with some value. And you can see here is some multiplication. Nice. Jump here, adding, so multiplication, adding, dword multiplication, so you can see it nicely XORing. So basically this is the decoding routine of the shellcode, because the shellcode, if you check it, it's really it's obfuscated and it's not readable. So what we can do, first of all, we can just get rid of this, because we don't need this. We just need here the start 1FE. 1FE is our start we are interested in. If you check the, we can just general and show me the opcodes, and we just try to find 1FE EA88. Open in 101 editor, and 1FE, I think it was 1F and E88I. 1FE. Oh, where is E88I? Here. Nice. So basically this should be the start of the shellcode. But if we don't, if we are not really sure about our assumption from the IDA, we can just close it and use another tool. We can use another tool which is basically very phenomenal when you want to emulate 32-bit shellcode, and it's called Shellcode Debugger. SCDBG. So go, this is my repository, and shellcodes, shellcode debugger, graphic user interface, and here is the shellcode. What you can do here is you can basically start offset is from 0 and find shellcode. Find shellcode is basically very interesting thing, because it will try, this tool will try to emulate all the offsets and will try to catch if some of this offset is leading to some Windows API, resolve Windows API and other things. I don't want to create dump for now, but launch it and check it. And you can see here many possible location. You can see that the final address is the same here, get proc address, it goes from all of this, but check it here, 1FE. 1FE was our first assumption from the IDA. So we just try to use the 4, here the option 4, run it, and you can see it's basically it. Yep, you can see what it does. Proc address, expand environment strings, public, vbcexe, the loading library URL1, get proc address, URL download the file, downloading the file to this location, and shall execute. Nice, and you can see that the starting offset is 1FE. So we really nicely confirm it. We can just basically again modify it in 101 editor, try to find the 1FE offset, 1FE, 1FE is here. You can see it here, 1FE, and just delete all of this, because this is what we don't need. And that's it. Save it. And this is all your shellcode from the beginning to the end. But you can see here nothing interesting, no strings, because it's obfuscated, it's encrypted, and we just try to deobfuscate it. we can just try to find strings here, and you can see nothing. Nice. What I want to show you now, it's really easy to use, but let's say it's really easy. So you can basically just drop it here, the shellcode, and you don't need to find the shellcode. Start from offset 0 and try to create dump. What you do with this option is basically it will emulate it, the shellcode, and all changes to shellcode, because it's a self-modifying code, it will decrypt some content, and after all of this, it will be dumped from the memory. The modified content of the shellcode already decrypted. Nice one. So we can check it. Here is the unpack one. If you check it in some hex editor, you can see that basically there are some strings as part of our environment. There are the strings related to Windows APIs, which gets called. So nice. If you try to now search for strings here, you can see here is immediately obvious what this shellcode is doing. Go library, get proc address, expile environment variable, URL download to file, shell execute, exit process, and you can see here is the another IOC, the last stage which gets downloaded. Okay, so this was pretty easy to do it in this way, but if you just basically would work, for example, with 64-bit shellcode, the CD debugger is not able to process 64-bit shellcode, so we can basically easily replicate the decoding things of the shellcode. Because if you throw it to IDA as a 32-bit, okay, again, edit, select all, unidentified, press U, and here is the start, so just press C. Here is the call, and you can see call to this function, text view. And as you remember, this is basically just pushing the next address, like 5, the 5 to the stack. The 5 is popped to the EBP, so EBP is pointing to the next address of 5, and EBP is containing the 5. It's jumping here, jumping here, jumping. Yep, it's here. And you can see here is the addition to EBP. EBP contains 5 and 1 5D, so 162. EBP now has 162 in hexadecimal. And you can see 162 in hexadecimal, jump, jump, jump. You can see EBP plus 297. So if you just run calculator, and you can see hexadecimal 162 is EBP plus 297. Hexadecimal 162 plus 297 equal 3F9, and 3F9 is almost end of the shellcode, 3F9 to here. So basically this to 162, this, from this to the end, it gets decoded. With the routine, we can see somewhere here. You can see here is basically counter. Yeah, the end of the end of the decoding routine, the counter, and here starts the multiplication. This multiplication basically confirms that EDI register is 0, because a multiplication with the 0 is 0, and here you can see basically it goes to here. Here is our multiplication with this constant value, jumping here, addition to EDI register again, and I think that the EDI register should be used in some XORing, and you can see here is the XORing with the current value in the address of EBP, so 162, 4 bytes. I XOR with the EDI, and you can see here is basically some moving next to the next dword to in the EBP until it gets to the location of the counter ends. So nice. Here should be some comparing. Yeah, counter with current value of EBP, and if the EBP is smaller, you can see it here, just continue, and if not, just run the decoded routine, because 162 is the location where the decoding starts. So jump to location 77, and again multiplication, and again. Nice. So now we understand how does it work. So what we can do next is basically we can very easily decode it to with by our own statically with help of Python. And for this purpose, I already prepared. Here is the decode shellcode, and you can see immediately what is going on here. You can see it just gets the shellcode. First of all, I will try to change the path. Copy path, and here we need the shellcode. And this could be the shellcode, but the decoded one. Decoded shellcode. And here you can see basically the constant which starts basically with 0, and what you can see loading the shellcode. The shellcode is just from the range 162. You know, basically there is starting the decoding routine of the shellcode to the length of the shellcode, and steps are basically 4 bytes, dwords. And here you can see the constant, multiplication, and addition. Yep, these are the two constants we saw already in the code, and converting from bytes, confirm that it's unsigned, and patching the original bytes. And these bytes are just will be written to new file. Just run it. And if we confirm it, this should be quite fast. Yes, and so you can see here the decoded shellcode. If you open it one-on-one editor, you can see it's already decoded. You can see nicely the strings here. Basically all what we did already with the SC debugger, shellcode debugger. Nice. Strings, and you can see the same here. The last stage URL. From basically the shellcode will download the vbc.exe file to the public directory, and it will execute it with the shell execute x. Nice. But if we don't want to emulate, I would like to show you one other thing. We can basically just grab the shellcode, which is encoded, copy it, and we will just convert it to, we can convert it to exe file. Debuggers, shellcode, and shellcode to exe. We will convert it. This is basically the encoded shellcode, but we can convert it. Shellcode, the bat file, and we just saying we want a 32-bit exe file. The file we want to convert to exe is shellcode.bin, and the output is xxx.exe. Enter, and it's done. Here you can see it. What you can do now is basically we can trace with tiny tracer, awesome tool made by HashRZ. So basically tiny tracer is based on pin tool, tracing tool, binary instrumentation tool, which is able to hook function, and it will basically tell you what function got called, and with all what parameters. If there are no arguments printed in the result tag file, just change the params.txt file. I will not be covering it here. So that's it. It's probably done. Yes, and sometimes it just happens that it's still hanging here around, so terminate it. Okay, here is the tag file, and if we open it in 101 editor, we just confirm that basically we can see the same output from the shellcode debugger. So expand environment variable, you can see here the environment variable, URL mon, low library, and get proc address URL download to file. Just remember this this API because I will show you later why it is important. And yeah. It downloads the file. Again, it will try to load library shell 32 because it will try to get proc address shell execute X and it will execute the sample. Nice. So this was another approach. The last one approach, which is most reliable and most, it works every time. Because this was like a little bit guessing where is the shellcode start and other things we have to know many knowledge, but what I want to do here is basically I will switch to my second VM and I will show you how we can do it in the normal way, how basically oh, I will explain it. Let's say here is the second VM, and basically this is the best approach if you are dealing. You can deal, for example, with 0 days and you are absolutely no chance to use some parsers or already built-in tools because they are not prepared for this 0 day. So how you can do it? You just know that this document is just spawning something what it shouldn't spawn. So we just try to attach the debugger and find the shellcode location to investigate more. So how you can do it? First of all, I would like to show you what's happened if you run it. So let's run procmon and run this document. And you can immediately see that something goes wrong. Some error happen. Yep, you can see it here. Okay, so just close it. And something strange. Okay. Procmon is here, just stop it, tool, process tree, and show me the process tree. First of all, you can see here is the Windows word, and I think that with the help of com object, basically the equation program is spawned to show you the equation table, which basically has the vulnerability, and you can see it here. So just copy this, because we want to, in this program is the one vulnerable. This we want to trace, this we want to debug, this we want here in this process is the shellcode. So just copy this name, close it, let's find it. Oh, first of all, jump to gflex, and why I'm using gflex, basically I would like to, if I run the .rtf document and Microsoft Office document, Microsoft Office will run, Microsoft Office Word, it will spawn the equation program. And I want to set the image file options thanks to the gflex, that I want to basically attach the debugger to all equation program, which starts with the file name I will show you. So I will go to the image file, copy the AQ and EDT32EXE, press tabulator to refresh, and here you can select the debugger. What gflex is basically doing is just setting the appropriate registry image file execution, I think, for this file name, and it will just saying the Windows operation system, hey, whenever the this EQ and EDT32EXE will spawn, just attach the debugger, which is the path is specified here. So just go to this. I would like to attach the 32-bit debugger to this. Okay, copy path, and here like this. Okay, apply, and okay. So now if we run it, you can see we have attached the debugger to the equation program. So let's continue to, and we are on the entry point. We are on the entry point, just check the symbols and you can see some symbols here, but there is not yet the URLmon, which basically is performing the download to file. So how we can do it? We can have many options. First of all, we can just go here and load library URLmon. It will be loaded, and we can set a breakpoint on the URL download to file W API function. If you just don't load it here into the debugger, you can't set a breakpoint on its API. So this is the first approach, and the second approach is basically go to options, preferences, and just check the system DLL load and DLL load, save, and continue. You can see that here is the MSI library, and here is another library, and here is another library, and here is another one, another one, another one, another one, another one, another one. Oh, I hope I didn't miss it. Come on. Okay, so once again, come on, go to entry point. Okay, system breakpoint, entry point. Okay, I just can't hit it. I don't know why. So cancel, and once again. Don't save it. Run again. And check the URLmon when it gets loaded. And here it is. Here it is. Don't ask me why we couldn't saw it before, but here it is. If you check it, first of all go to option and uncheck the option DLL load and system DLL load. Save it, and you can see here somewhere URLmon, and now find the URL download to file W here. And I already preset the breakpoint here, but remove. We just set here the breakpoint. Go to breakpoints, and you can see here we have the breakpoint. Oh, I don't know what it is, but here it is. We set the breakpoint on the function. Let's continue. And we also uncheck the options of the DLL load breakpoints. Continue, and we hit the breakpoint URL download to file. This should goes from the shellcode. So just check the call stack, and in the call stack you can see the location from where it got called. Here we can see call EAX, and EAX just pointing to URLmon, URL download to file W. Okay, and what is this? This is the shellcode. So if you just, for example, search for some undirect calls which get resolved during the runtime, just here is call EAX, here is call EAX, here is call ESI, call EAX, and this is probably all. Call EDI and continue. Next is shell execute. You can see shell execute, and shell execute is quite a strange function because there is only one argument which points to structure and other things, but I can show you. Basically, if we just grab the first argument, shell execute, follow in dump, follow the word in current dump because it's a pointer to structure. So here, and this is basically, it looks very strange, but this is basically structure. And here is, I think, this is the file name which gets executed. I think you can again follow the word in current dump because it's a pointer, and you can see here is the file. Nice. And that's it. We are basically debugging the shellcode, and again, you can just again try to find a location before or in the start of the shellcode and other things. But this is basically a very good approach how you can do it, very reliable. Nice, that was all. But now, okay, close. Don't save here. So I will switch back to my second VM and we will continue. So now we absolutely cover the first stage, the Microsoft Office document, the RTF, which gets downloaded by the external reference, and we cover the shellcode, which is basically injected and executed via a vulnerability, and we examine, reverse, and basically analyze the shellcode. We don't know absolutely what the shellcode is doing, and the last stage is basically the last stage which gets downloaded, which is this wbc.exe file. Just copy that, and here. So now, first of all, I will throw it to PE Studio because I want to show you something. Yes, first of all, again, we already checked it, but it's if it's a very executable file. It looks like executable file. So let's continue. Detect it easy again. You can check it's a 32-bit. It's probably written in Visual Basic. Nice, and it's very large. It's like the size. It's somewhere here, and it's so large. It's about 1 megabyte. Yep, 1 megabyte. And you can check also exe info, for example, for some honor. It's honor very good tool. Again, Visual Basic. So my first assumption is that this is basically some kind of wrapper or a packed binary where the basically wrapping code is written in Visual Basic, and the AgentTesla or another payload will get decrypted during the runtime or unpacked during the runtime and gets executed. So let's check it in PE Studio. First of all, you can see VirusTotal is immediately telling you that it's probably AgentTesla. You can see AgentTesla and AgentTesla. Okay, what is next? What could be interesting? First of all, resources. There are many resources, but none of them is quite interesting. So we can see the libraries, Microsoft Visual Basic, and imports, no imports. Okay, that's quite normal for Microsoft Visual Basic, but what we can see here in the strings, for some machine learning, artificial intelligence sorting of strings, I highly recommend to use PE Studio as an initial assessment, malware initial assessment, or a combination of string zifter, flare strings, and rank strings, because it's very nice. And what you can see here, blacklisted, it will be very fast. You can see blacklisted, you can see many something strings related to decryption, API function of AdWP, and decryption, crypt decrypt. Absolutely think, I really think that crypt decrypt should be our first thing what we should check. Yeah. There are many other strings, but basically it's wrapped in some kind of a messy code which contains very not interesting things, but we want to get the final payload. So crypt decrypt is basically our point of interest. Nice, we can just throw it to debugger. File, open, and open me the file. Desktop. Here, wbc.exe open. Come on. Options, preferences. Yep, there is everything what I need. And now I want to jump to the entry point. I'm on the entry point. I have some already downloaded. I highly recommend to download the symbols, but it's just a matter of your choice. And what we can do now. Crypt decrypt was basically our main point of interest. So we can try to set breakpoint on crypt decrypt. set bpx, and on crypt decrypt. Yeah, breakpoint is set. That's good, because if it's an error here, it basically means that the adwp DLL is not loaded now. So basically, you should jump here and load the library adwp and set a breakpoint on the crypt decrypt. But in this case, the adwp is loaded. You can see it here, somewhere here. adwp, yeah, you can see it here. So it's already loaded, and we set the breakpoint on crypt decrypt. Nice. So let's continue, and we hit the breakpoint. Surprise, surprise. And first of all, crypt decrypt, I think that crypt decrypt has 6 arguments, so we just make here to visible 6 arguments. And first of all, these are some H keys and handles and other things, but here should be the buffer, the 5th argument, and here should be the size of the buffer. These are pointers. It's obvious. Basically, you can see here, this should be the 6th argument, and this should be the length of the buffer which gets decrypted. So you can see here, follow the word, because it's a pointer in current dump, and you can see the length is, if you check it here, 36200 in hexadecimal. 36200 is the length of the buffer which gets decrypted. It's very important. 36200. And here is the buffer, again followed in follow the word in current dump, because it's again pointer, and this is the buffer which gets decrypted. So we can confirm it, just debug and execute till return. And it's decrypted, and it's exe file, maybe the last stage module. So what we can do now, we can just basically check that it looks like all is decrypted. Nice. So we are here on the start, and right click, and I'm using quite a nice plugin which is called X select block, and here is the start and end address. I don't want to use end address, I want to use length, and I checked here in hex. So 36200 was the length, if I remember, 36200. Okay. And now right click, binary, and save to file, and we can save it as on the desktop as dump.bin. Okay, 36200, I think it was. Hope I was right. Follow the word, follow in dump, and yeah, 36200. And that's it. I think we have dumped it here. And if we check it with some, for example, detect it easy, it will tell you that it's .NET. It's a .NET assembly. Nice. So it should be correct. We can close it. Nice. And here, first of all, did we dump raw binary, or was it already mapped in memory, virtually mapped? We can confirm it quite easily. If you check in hex editor, you can see that basically here is the text section, these are the section, all the code of the text section is already starting. There are no null bytes, like very large null bytes, because usually when the program is virtually mapped, the text section is starting from a hexadecimal offset like 1000 or 2000 and other things. But here you can see that it's basically starting immediately, I think, in this location. If you don't trust it, just rename it to exe file. And other very cool program for this, if we have virtually mapped or unmapped exe file, is pbur. pbur, one of the best PE viewer, and you can see, check the sections, and you can see that raw, it's nice. The text section is starting 200 in hexadecimal, and virtually is 2000. So we have raw format of the assembly, no virtual map. So we have everything prepared. You can see import Muscori, and basically it's telling us that it's .NET assembly, and okay. So we can start to investigate this. If we check it again in detect easy, you can see that it detects some obfuscator and .NET. Basically this is the AgentTesla final payload, but it's in some kind of obfuscated form. Wall and the main deobfuscation process I basically covered in my previous video about AgentTesla. So if you want to refresh it and learn some new tricks about deobfuscation, just check them. But for now, I will just do it in a dirty and quick way. I will be using dnspy and also d4dot. So first of all, just grab it here and go to entry point, and in the entry point you can immediately see that basically there are some obfuscated strings. So basically you have nice readable binary. The assembly, the code is readable, but all strings are obfuscated, so you can't see here anything. But you can see here are the obfuscation, the strings obfuscation. Basically, this namespace and this class is responsible for all string obfuscation. You can see if you double click on, if you click on the method, you can see here basically when this string gets used, it will call this method in this class, in this namespace, and decrypt that string and use it. And it's all defined here. Here is the namespace, here is the class, and here is the method responsible for the decryption strings, and here you can see something. We will try to dynamically invoke or delegate these methods, all of them. So check the token, because it's very important argument for we will be passing to the d4dot deobfuscator, which is able to delegate or emulate our methods and replace the strings in the location where it gets called to decode it and other things. So you can see 0600022E, and you can see 22F, 230, 231, it just increasing one by one. And the last one is somewhere here, the last one is here, 343, 542 is last one. So we need to use this metadata token of this function. Nice. So let's close it, file, close. Again, if you wanna spend some more time with the obfuscation routine, just check my previous videos. For this purpose, I already prepared here the token generation, because we will need to generate the command line arguments for the d4dot, and it's quite difficult. But we will use the Python, so it will help us a lot. So let's start the Visual Studio, and also let's start the d4dot malware tools, d4dot deobfuscators, .NET deobfuscators, d4dot, here it is. And I will copy the dumped exe file to here, and here I will prepare PowerShell with the command line arguments for d4dot. d4dot, let's tell me what I should do. d4dot, here the file, and here. So we will prepare this one. We will replace the file name with our dumped exe file. String type will be delegate, and if the delegation is detected, you can use the emulate string type of decryption. But for this purpose, it's okay. And here you can see string token, the metadata tokens of the methods which are responsible for the decryption routine of the strings. I already tell you. So we need to generate. You can specify here as many as you want. So you can use this script will be also available on my GitHub page. So here somewhere, generate tokens will be, yeah, this will prepare our generation of tokens to deobfuscate final payload via d4dot. String type delegate and string token are here. So I will just generate the tokens for the command line use. And this should be okay, just run it. and it will create for us new file which is called tokens.txt, and yep, also print it, and that's all, we don't need it anymore. And here should be somewhere tokens. If we open it, you can see here is a prepare the command line. So just copy, and 3542 is last one, if you remember, and 22E was the first one. Copy it and just go to PowerShell and paste it. Nice. You will prepare the command line, and after that we will just basically run it. Come on. Yep, it's already done. So run it, and it will deobfuscate our last stage payload for us, the default awesome tool. We can close it. We have it somewhere here. Dump, we are not interested in the dump, we are interested in the clean one. Yep. Here, throw it here. dnspy, just check it here. Dump cleaned. Go to the entry point, and you should see that the strings are already decrypted. Nice, you can see it immediately. Here is the persistence and other things. Nice. What you can do next is basically go to this class, to this namespace, because this is basically the decryption routine, which wouldn't be used anymore because all strings are already decrypted. So you can just right click and delete the namespace. Go to file and close the file. Save the module. Save it to the original one. Okay, and that's it. Again, jump to the entry point, and you can happily analyze the deobfuscated, decrypted, prepared for analysis agent Tesla, which is basically very, very, very trivial, because we have now they revealed all the strings. So for example, if you just close it, we already patched this binary, because check the size is very small. Now what you can do is basically print all strings, and according to the strings you can just basically guess what is the activity of this program. Yeah, you are seeing many interesting strings, and now is the time that our another tool could shine a little bit and help us. Flare strings, we will just extract all strings. Flare. Okay, command line. So let's switch to PowerShell. Flare strings, dump, cleaned, pipe, and rank strings, and good. Throw it to strings txt. Yep, and it should be very fast. And done. If you check the strings here, yep, you can see immediately the strings. Okay, here of interest, you can see the Tor browser, you can see some other APIs, the dynamic DNS, some FTP, and many things. This could be quite a nice to investigate. You can see again many strings related to password stealing, credential stealing, Windows credentials, FTPs programs credentials, VNC programs credentials, mail accounts credentials, web browser credentials, and many things. So basically steal. But I covered it already in my previous videos. So that's it. That was malware analysis flow of the agent Tesla from the initial compromise file, which basically this file usually is delivered via email attachment. You should investigate this, and basically this is most of the time it's a everyday job of the malware analyst, and I hope you enjoy this. I hope you learned some new things, some good workflow. I hope it was quite clear everything and you enjoyed this. Thank you for watching and see you next time.